Okay, so here's the Zoom meeting for Physics 232C. This week we're studying Chapter 19, which is on electromagnetic induction, a phenomenon that we use every day because that's how we make electricity. So you should read the chapter. Most people have already finished the reading quiz, so they've already read the chapter. Take notes. That's very important. So you should have a notebook and write down the most important equations, other kinds of notes. Most of your notes will just be equations. So here are some of the equations that you should understand. For example, Faraday's law. Michael Faraday, the great Michael Faraday, discovered electromagnetic induction, how to make electricity from magnetism. And we can summarize his experiments by saying the electromotive force around a closed loop is equal to the rate of change of the magnetic flux going through the loop, or actually the negative rate of change of magnetic flux through the loop. The minus sign determines the direction of the EMF. Is it clockwise or counterclockwise? Here's the basic equation. It looks very simple. It's not as simple as it looks. What's phi? What's E? But this is something that was very, very important to the development of electric technologies, because it provides a way to create an electric field. There's a section on motional EMF. Perhaps the flux changes because a conductor is moving. So if a conductor moves through a magnetic field, there's an electromotive force or a voltage difference from one end of the conductor to the other. There's at least one, I guess there's one section on important technologies. For example, the electric generator is a coil of wire rotating in a magnetic field. That means the flux of the magnetic field through the coil is changing in time. And so there'll be an alternating electromotive force around the coil. That's how we make alternating currents. So that's the electric generator. We'll see an example of that in a few minutes. A transformer is a piece of apparatus which is everywhere. I mean, you just have transformers everywhere of all different sizes, from small transformers that you might plug into a wall socket to enormous transformer substations the size of a house. All around the countryside, you'll see little green boxes, little green metal boxes with a warning: don't open the door. Shocks from those transformers would probably be fatal. Then the last part of the chapter is on something that we use in electric circuits, which is inductors. An inductor is just a coil of wire. A solenoid is an inductor. So that's all an inductor is just a coil of wire. The inductance is defined as the magnetic flux divided by the current. That's the self-inductance. And then there'll be a voltage change around the coil equal to minus d phi dt. That's Faraday's law, which I can write as minus L di dt. So if you put one of these in a circuit, if the electric field is changing, then there'll be voltages developed throughout the circuit, proportional to the rate of change of the current. Now, of course, our lives are full of circuits with changing currents in the form of alternating current circuits. In an alternating current circuit, the voltage is alternating in time sinusoidally, might be V0 cosine omega t. The current in the circuit will also be alternating in time, so it's called alternating current, with the same frequency, omega. Omega is the angular frequency. There may be a phase shift, and there'll be some amplitude of current oscillations. In DC circuits, the voltage is the current times the resistance, R. So V is IR. That's Ohm's law. We've studied that before. In alternating current circuits, it's more complicated than that. First of all, there's this phase change, and then there's the amplitude change, or the amplitude ratio between voltage and current. So V0 is I0 times the quantity Z, which we call impedance. And contributing to the impedance will be resistance, capacitance, and inductance. So there's a whole section on AC circuits. Now let's go over some example problems and see how these equations, which you should have written in your notebook, how they are used. This problem has a circular coil of wire has N turns, radius A, and resistance R. A magnetic field perpendicular to the coil is increasing at a rate dB divided by dt, or change in magnetic field divided by change in time. That's the rate of change of the magnetic field. Write that as delta B divided by delta T. And then the question is, find the induced current in the wire. And some things are given, like the number of turns of wire, the radius, I guess, is A, the resistance, some number of ohms, rate of change of the magnetic field. Now, this isn't an alternating current. This is just a current. This is just a case where the magnetic field is changing linearly in time, not alternating. So to solve this problem, as usual, we draw a picture. So here's a picture. A coil with N turns of wire. And there's a magnetic field passing through the coil. The wire from one end to the other has a resistance R. And now we want to calculate the EMF around the coil from one point around to the other point, from one end around to the other end. So there's the picture. And next we write down the relevant equations. Well, this is going to be a straight example of Faraday's law. The electromotive force is actually negative, the rate of change of the flux. And the flux is the magnetic field times the area. But because this has N turns of wire, there's a flux B times A through each turn of wire. So through the whole coil, from one end to the other, there'll be N times the flux through one turn. So the total flux will be N times B times A. And then, of course, Ohm's law says I is E over R. So this electromotive force will drive a current. in the wire. And the size of that current will be this electromotive force divided by the resistance of the wire. So I is E over R, that's 1 over R d phi dt, not worrying about the sign. We're just calculating the size of the current, not the direction. So that's 1 over R d phi dt. Now phi is NAB, so the change in phi would be the change of NAB, but N and A are constant. N is the number of turns, A is the area. So the change in NAB will just be NA times the change in B. And we divide by the time. So here's the rate of change of the magnetic field, which is given. So now we start plugging in numbers. N is 15, A is pi, R squared. The change in the magnetic field per second will be 0.11 Tesla per second, that's given. And we divide by the resistance, that's given, 0.24 ohms. So that's the calculation we have to do, that's the answer. I, that's what goes in a box. As usual, it's a number with a unit. We can figure out the number with a calculator, but we can't figure out the unit with a calculator. We have to look at the units. So here we have meter squared Tesla divided by seconds divided by ohms. Tesla meter squared per second divided by ohms. Now a Tesla is a volt seconds per meter squared. So the numerator here is volts, and volts divided by ohms is amps. So the unit will be amps. And now what's the number? Well, here's 10, here's a power of 10, 10 to the minus 4 when you square it. Here's 10 to the minus 1. There's another power of 10 to the minus 2. There's 1 over 0.1. So if you add up all the powers of 10, it's sort of like 10 to the minus 5 amps. And that's what'll go in the Lon Kappa's answer box. Let's look at another problem. So here's the problem. It has an AC power supply and a resistor. So it's an AC circuit with no capacitance, no inductance, just the power supply and a resistor. And the RMS electromotive force, or the RMS voltage, we'll call that VRMS. The current is, there's no phase shift if there's no capacitance or inductance, so the phase shift will just be sinusoidal with a value I0, which would just be given by Ohm's law. So you have 3 parts. There's part A, part B, part C. And you're given, actually, you're given the size of the current. You're given the angular frequency, omega, in this alternating current. And you're given the RMS voltage. So the voltage as a function of time will also be an alternating function, V0 cosine omega t. With the same frequency, same angular frequency. All right, so as usual, we start by drawing a picture. So here's the picture. Here's the power supply, but it's an alternating power supply, an alternating voltage. So at some particular time, this terminal might be positive and this terminal would be negative. Half a cycle later, this terminal would be positive and this terminal would be negative. So the polarity of the terminals, the electrodes, will be alternating. plus minus, minus plus, plus minus, minus plus. It'll be alternating. And that will drive a current around the loop and through the resistor, which is alternating. So you have alternating current. Now, what you're given is that it has a alternating, or it has a, what does it say? An AC power supply. So the voltage as a function of time is V0 cosine omega t, where V0 is the amplitude. The RMS voltage is the root mean square voltage. You take the square of this and take the average in time. Well, the square of this will be V0 squared. And the average of cosine squared, cosine alternates between +1 and -1. Cosine squared alternates between 0 and 1. The average will be a half. So the mean square voltage will just be V0 squared times a half, or the root mean square voltage will be the square root of that. It'll be V0 over the square root of 2. And similarly, there'll be an alternating current with some amplitude I0 and the same frequency. And again, the root mean square current will be the maximum current, or the amplitude of the oscillations, divided by the square root of 2 in the same way. All right, so you're given the maximum current, you're given the frequency, and you're given the RMS voltage. So, for example, part A is to calculate the RMS current. Well, the RMS current is always the maximum current, or the amplitude, divided by the square root of 2. So 1.35 over the square root of 2, that'll be something like a little less than 1, say 0.9 amps. So that's this box. The second part is to calculate the resistance. Well, in general, resistance is voltage over current. So for example, it's the maximum voltage over the maximum current, or it's the RMS voltage over the RMS current. Those are all equal. We know the RMS current, that's given, 110 volts. That's the standard RMS voltage in a wall socket. In part A, we calculated the RMS current, that's 0.9 amps. So we'll have 110 over 0.9. It'll be something a little bigger than 110, let's say 120. And the unit will be volts per amp, that's ohms. So that solves B. Now, part C is to calculate the power delivered to the resistor. You know that when current flows through a resistor, it causes the resistor to emit energy in some way. For example, it can convert the electric energy into heat, and the resistor will heat up, it will get hotter, temperature will increase. Or it can produce light. That's what an electric light bulb does. So what's the average power? The power will be changing in time because the current is changing in time. So the power will be going to a maximum value to 0, to the maximum value to 0. It'll be alternating between some maximum value and 0. Now we want to know the average power. So you just average Remember, power is I squared R. So the average power will be I RMS squared over R. And that's what goes in C. And as you see, I is about 1, R is about 120. So I squared R will be something like 100. And what's the unit? watts because it's a power. Here's a problem about a electric generator. Everyone owns an electric generator. Well, no. Everybody with a car owns an electric generator. It's called the alternator. You're probably too young to own a car, but your parents maybe own a car, and they'll have an electric generator that they drive around to keep their battery charged. So the statement of the problem is a car alternator produces peak voltage V0 to charge the 12-volt battery. Suppose the alternator coil has a diameter D and it's spinning at 1200 revolutions per minute in a magnetic field B. That's how electric generator works. There's a magnetic field. There's a coil of wire. It's spinning around. It's rotating. It's spinning around. The flux of the coil is alternating. You know, in one orientation, it has a positive flux. Half a cycle later, it has a flux in the other direction, so it has a negative flux. So the flux is alternating between positive, negative, as the coil rotates. So by Faraday's law, there'll be an electromotive force around the coil. And what this question asks is, how many turns of wire are required to produce a peak voltage of V0? Now, V0 should be greater than 12 volts so that the battery can be kept completely charged. It specifies here that the peak voltage will be 14 volts. The diameter of this coil will be 17 centimeters. It'll rotate, well, it says here 1200 revolutions per minute, but that's being changed here. So this is revised. Let's say it's 1340 revolutions per minute. And it's in a magnetic field. How strong is the magnetic field? Well, we'll say 0.16 Tesla. So you have written in your notebook the equation from reading the chapter. The EMF in a electric generator is NBA omega. Now B, well, B times A, let's say, is the flux through the coil. So that will be B times A times the cosine of omega t. Because when the coil is perpendicular to the magnetic field, then you'll have a flux of B times A. That corresponds to T equals 0, or 2 pi, or 4 pi, or 6 pi. When the coil has turned over half a cycle, then you'll have flux in the other direction. So the sign will be the opposite sign. And it'll alternate between the different directions, so you'll get an alternating electromotive force. So actually, this equation is probably should be, if this is going to be for arbitrary time, this should be multiplied by sine omega t. So it's an alternating electromotive force, or an alternating voltage. Alternates between this positive value and the negative value, as the sign alternates between +1 and -1. So this formula in black would actually be the maximum electromotive force. That occurs when the sign is 1 or -1. So in fact, NBA omega, that's the quantity you have to put in this box. NBA omega. No, that's not what you put in the box. You want NBA omega to be 14 volts. That's V0. What goes in the box is N. So I have to solve this equation for N. So we always do these problems the same way. We draw a picture. We use the picture to write down the necessary equations, and then we start doing calculations. Now, the problem doesn't tell you omega. It tells you the angular velocity of this rotation. 1200, or actually changing that to 1340 revolutions per minute. So the first thing you have to do is figure out omega. Omega will have units of radians per second. If you use it in the equation, we're not given omega in radians per second, but we're saying it spins around 1,340 revolutions per minute. So the first thing we should do is convert omega 1,340 revolutions. Now, one revolution is 2 pi radians. Divided by a minute. 1 minute is 60 seconds. So you see the unit now is radians per second. So that's going to be radians per second. And it's going to be something about 134. You don't want to do this accurately with a calculator, but just for the purpose of the Zoom meeting, I'll just kind of make an estimate. Now we want to solve for N. That's what belongs in the box. Oops. So N will be E max, that's 14 volts, divided by BA omega. B is 0.16 Tesla, A is pi r squared. The diameter was 17 centimeters, so that's pi 17 over 2 squared. Centimeter squared, we'll convert that to 10 to the minus 4 meters squared. And then BA omega is in the denominator, so omega is roughly 134 per second. So as usual, we have a number with a unit. We have to figure out the unit separately. I have volts divided by Tesla meters squared divided by seconds, Tesla meters squared per second. Now a Tesla is a volt second per meter squared. So the denominator here is volts. 1 Tesla is the same as 1 volt second per meter squared. So this will be volts. Volts in the numerator cancels, so there won't be any unit. There's no unit because we're just counting a number of turns of wire, so that doesn't have a unit. As for the number, well, you'll want to calculate this with your calculator, but you know, we can just sort of estimate. Here's a power of 10. Here's 1 over 0.1, so that's another power of 10. Here's more or less 10 squared in the denominator. So that'll be 10 to the minus 2 in the numerator. Here's 10 to the minus 4 in the denominator. That'll be 10 to the plus 4 in the numerator. Here's 100, so that's another factor of 100. And so we get, you know, more or less 100. Okay. Let's see, how many more do I have? Whoops. Okay, we did that one. There are 2 more here. Opening a switch in a highly inductive circuit can be dangerous. To see why, consider a 6-volt battery supplying current I to an electromagnet with inductance L. So what's an inductor? An inductor is just a solenoid. So for example, an electromagnet is an inductor. An electromagnet would have a coil of wire, and it would be filled with, I suppose, iron. I can't do that. Let's see, what do I have to do? It would be filled with iron, an iron core, to create a strong magnetic field. That makes it an electromagnet. So there'll be an electromagnet, a magnetic field coming out that direction, an electric field coming in this direction. A strong magnetic field inside the solenoid, so that will carry a whole lot of energy. Now, we want to consider a 6-volt battery used to create an electromagnet. That's when the circuit, the switch is closed, so I have a complete circuit, and I can have a current. Current can only exist if there's a complete circuit. Well, there'll be a complete circuit if this switch is closed, complete loop. The current has to go all the way around the loop, from the positive terminal of the battery back to the negative terminal of the battery. Now, if we open the switch, then there can't be any more current, because there's no way for the charge to get from the positive terminal of the battery back around to the negative terminal of the battery. So that means the current will go to 0 when I open the switch. And if the current is 0, then there won't be any magnetic field here. This is no longer an electromagnet because it doesn't have any current. It's just a coil of wire. But magnetic field has energy. So where did all that energy go? It's got a large amount of energy from magnetizing the iron core. When I open this switch, all that energy is gone someplace else. Where's it gone? After all, as a general principle of physics, energy is always conserved. So what happens when the switch is opened? When the switch is closed, there's a current and a field energy in the inductor. When the switch is open, there's no current. What happened to the energy? There's all that magnetic field energy inside the solenoid. Well, the answer is there'll be a spark here. That current will pass, it can't pass through the conductor, it has to pass through the air. So there'll be a large enough electric field to cause a spark in the air in the neighborhood of the circuit, of the switch. And that spark will be very hot. It'll emit light. You know, it'll be a spark of light. So it'll emit energy in the form of radiation of light and heat. Now, why is that dangerous? Well, here's the picture. Now let's write down the necessary equation. The equation is that the potential difference between the two terminals on the switch, so let's call that delta V, the potential difference between the two sides of the switch, will be equal to the potential difference across this inductor, and an equation you've written down in your notebook from reading the chapter. The potential difference across an inductor is L delta I over delta T by Faraday's law, where L is the so-called inductance. So here we're given I, we're given delta T, we're given self-inductance. So we can calculate this voltage difference at the switch. So, you know, at this point, we've drawn a picture, we've written down the relevant equation. Now it's just a matter of doing the calculation. with a calculator, as usual, there's a number with a unit. L is 2.6 henries. Delta I is 2.5 amps. Delta T is 0.68 times 10 to the minus 3 seconds. That's the time it takes to open the switch. So we have a number here, 2.6 times 2.5 divided by 0.68. But this is 0.68 milliseconds. So I have a power of 1,000 in the numerator. And then the unit will be H times A per second. So we have to figure out what's the unit. Well, inductance is flux over current. The unit of inductance is henries, H. Flux is magnetic field times area, so that's Tesla meter squared. I is amps. So we have here HA over S. HA is Tesla meter squared, so HA over S is Tesla meters squared per second. And a Tesla is a volt second per meter squared, so that's volts. So the unit will be volts, and the number will be about 1,000. Or actually, this is a power of, let's see, this is a power of 6.3 or 0.68. So that's not right. It'll be yeah, that is right. Or maybe it's 1,000. Maybe it's 9,000 volts. In other words, a very large voltage, dangerously large voltage, will generate this spark. And that's why dangerous. Now let's see, got one more problem to go over, but are there any questions? Let me see if there are any questions in the chat room or in the chat box. I don't see any questions in the meeting chat. Anybody want to just unmute your microphone and ask a question? All right, so let's see, we have a little bit of time left. So let's go over one more problem. In a simple AC circuit, the voltage is 110 volts AC at 60 hertz. That's the American standard. That's the voltage and frequency or period of oscillation that you get in a wall socket. Let's say the circuit has resistance R. And then the problem is to calculate 1, 2, 3, 4, 5 properties of this circuit. So here's the picture. We always draw a picture first. Well, here's the picture. There's, you know, what's supplying the power? A plug. You plug the circuit into the wall. So here's the wall. Here's the plug. The frequency and RMS voltage between these two sides of the, you know, a plug has 2 wires. It's got these 2 little terminals. So between the 2 terminals, we'll have an alternating voltage with an RMS value of 110 volts. And it alternates with a frequency of 60 hertz, 60 cycles per second. This is what's supplied by the power company. This is what you supply. This is your This is your apparatus that you're plugging into the wall. And it only mentions the resistance. So we want to calculate various properties of the circuit. So here we've drawn the picture. Now let's write down the equations. The voltage is alternating. So it's some amplitude V0 cosine omega t. Now V0 is not 110 volts. 110 volts is VRMS. So if we take V and square it, then we get V squared. That's V0 squared cosine squared. Now, if we take the average of both sides of the equation, the average of V squared will be V0 squared times the average of cosine squared omega t. As t changes, cosine squared will alternate between 0 and 1, because cosine alternates between plus and minus 1. So cosine squared alternates between 0 and 1, and the average value will be a half. And if I took the square root here, that would be the root mean squared. Or I could say that this quantity is the root mean squared squared. It's V0 squared over 2. So now take the square root of both sides of the equation. VRMS is V0 over the square root of 2. So the first question is, part A, what's the maximum voltage? Well, the RMS voltage is 110 volts. So the maximum voltage will be V0 times the square root of 2 by this equation. No. Let's go back. Will be, oh, looking at this, the maximum voltage will be V0. And looking at this, that's the square root of 2 VRMS. So that's the square root of 2 times 110 volts. And that's about 150 volts or something. It's about 160, I think. So it's about 160 volts. Well, you know, do it accurately with a calculator. But that's what goes up here. 160, I guess it's 169 volts. That's the maximum voltage. But of course, the voltage is alternating between 0 and between that positive value and the corresponding negative value. So that the RMS voltage is 110. So that's A. Now, what does B ask for? The RMS current. What's I RMS? By Ohm's law, I is the voltage divided by the resistance. So the resistance is the RMS voltage, that's 110 volts, divided by the RMS current. Oh no, I already know R. Sorry. It's this 169 volts divided by R. And here it tells me the value of R, 300 ohms. The unit is volts divided by ohms. And the number is 169 divided by 300. So that's like 1.6 over 3, call it 0.5 or something. So this is something like 0.5 amps. Roughly. I mean, do it accurately with your calculator. So that's part B. Now, there are two more parts. Maximum current, power dissipated in the resistance, and average power dissipated. So you got three more parts here to do. And we have the equations for AC circuits. All right, so let's see. Are there any more? Okay, so that's everything. Any questions? Let's see. There were a couple of questions on the meeting chat. Can we just go over the unit part again? Let's see. Which problem? In all problems, there's a calculation of the unit. This unit? This unit? Let's look at this unit because it's a little complicated. Here we have.
Yes, it is this one.
Okay, let's see what we've got here. We take this equation, we put in E, B, A, and omega. So here are the units of E, volts, B, Tesla, A is meter squared, it's an area, omega is radians per second, but we don't need to carry the radians along. Radian is not really a unit, it's really a ratio. So we can just write that as inverse seconds. So we have volts divided by Tesla meters squared divided by seconds. Now you remember the electric force is QE, and the magnetic force is QVB. Now these have the same unit, newtons. These have the same unit, coulombs. So these have to have the same unit. So the unit of electric field, that's volts per meter, has to be equal to the unit of V times B, that's meters per second times Tesla. So Tesla, if I multiply both sides of the equation by S and divide by M, Tesla is volt seconds per meter squared. 1 Tesla is 1 volt seconds per meter squared. So this unit will be V divided by Tesla is volt seconds per meter squared times meter squared divided by seconds. Now the meter squared cancels, the seconds cancel, the volts cancel. So the unit is just 1. In other words, there is no unit. It's just a pure number. Any other questions? You can either type it into the meeting chat or just unmute your microphone and speak up. All right, so this assignment is due, I guess, Wednesday. So that'll finish chapter 19, electromagnetic induction. So this problem assignment is due Wednesday. And then we have chapter 20. Now we're going to spend 2 weeks on chapter 20. We're going to divide chapter 20 into 2 parts. Chapter 20 will have 1 part on electromagnetic waves. That'll be part 1. And then another part on the theory of relativity. So that's part 2. So, you can start reading chapter 20, but the problem assignment is not due till after spring break. And that will be part 1 of chapter 20. Part 2 of chapter 20 will be the next week. And then we'll have another exam. So the second exam will cover chapter 19, which we're finishing this week, and then chapter 20, part 1 and part 2, which will be after spring break. And then we'll have exam number 2. Well, let's see, it's 7:50, so we spent a little more than 45 minutes. It's about the right amount of time. So let me stop the recording.